Good evening and welcome everyone to the fifth event in our 2024 public speaker series, The Journey of Australian Science, tracing our history, discovering new paths, emphasising the importance of many of the distinguished scientists who have graced this hall. I'm Oliver Mayo, I'm a fellow of this academy, one of the conveners of the series, along with Professor Susanna von Kemmerer and Associate Professor Raphael de Michelis. Tonight we're on Ngunnawal country, and I'd like to acknowledge and pay respect to the traditional owners of this land, as well as those of all the lands on which our online audience may be joining us tonight. As we share our own knowledge, we pay respect to the knowledge embedded forever within the Aboriginal custodian of country, unceded land that it is. Thank you for being here at the Shine Dome tonight, and thanks for those who join us online. Tonight we're reflecting on the work of Sir Mark Oliphant, a truly great Australian physicist whose work probably contributed more to applied physics throughout the world than anybody else in terms of its influence. He's a South Australian, and I recommend, as a rattling good yarn, Wizards of Oz by Brett Mason, which tells you about him and another Adelaide lad, Howard Florey. It's fair to say that Oliphant's work was important in understanding how atomic nuclei merge and release energy. He worked innovatively on particle accelerators, particularly cyclotrons, revolutionised some of the experimental methods in nuclear physics, and advanced our ability to probe the fundamentals of matter. In addition to that, in many ways more important, he played a key role in the development of nuclear technology during World War II, particularly bombs. I think it's fair to say that without him, the Manhattan Project would not have taken the form it did and would not have begun when it did. Many US historians have written him out of the history, and that's why I recommended that book, which is a way into it, though a racy and not totally accurate read in itself. Oliphant's leadership extended far beyond his scientific work as such. He was a brilliant organiser of teams, groups, and organisations in general. He was the founding president of this academy and served for 6 years, from 54 to 60. He advanced the scientific community in Australia, promoted research, fostered collaboration. His presidency helped establish the academy as a leading institution for scientific excellence and innovation in this country. He had the ear of government, which is quite hard to get in the present times. Anyway, tonight our two speakers, you don't want to hear from me, will highlight the work of Oliphant, his long-lasting impacts, and share with us how his legacy has inspired their own work. And we couldn't have picked a better day for it, because even though he lived to 98, Mark Oliphant didn't quite live to 123. If he had, we'd be celebrating his birthday today. And in this context, I'd like to acknowledge some special guests with us tonight. Mark Oliphant's daughter-in-law, Monica Oliphant, herself wind scientist and enthusiast, Mark's grandson, Michael Wilson, Mark's great-grandson, Sam Wilson. Thank you all for being with us tonight and for your continued support of the Academy. Now, a reminder before I introduce our first speaker that if you'd like to join the conversation on social media, the hashtag is #SharpScienceJourney. As usual, there'll be Q&A with both speakers at the end of their second presentation. So if you have questions, answer them by raising your hand here in the theatre or scanning the QR code that will appear on your screen in the event. For those at remote locations, your questions will be read out by one of the microphone holders. So now let's hear from Professor Nanda Dasgupta. Nanda is an experimental physicist and director of the heavy ion accelerator facility in the Department of Nuclear Physics here at ANU. Nanda is a world leader in measuring and understanding the complex quantum interactions occurring in collisions of heavy nuclei. She was the first woman to be tenured in the Research School of Physics at ANU, was elected a fellow of this academy more than 10 years ago, and currently sits on the National Science and Technology Council. Please welcome Nanda.
Thank you very much for the kind introduction, Oliver. It's such a huge honor for me and my colleague, Dr. Ed Simpson, to be a part of this series of talks, which takes us on a journey of great Australian scientists and their contributions and the impact they continue to make in the future directions of the science that they chose to do. It is particularly significant that we are talking about Sir Mark Oliphant and nuclear physics on this special day. As you heard, it's his birthday today. And Oliver said, Sir Mark Oliphant was a great scientist, an innovator, a great experimentalist, and someone who had a very strong conviction of that science should be benefiting humankind and for peaceful uses of science. And Mark Oliphant, as we heard, recognized the need of a learned academy for Australia to bring together the best minds and discuss science, popularize science, and represent Australia elsewhere. For me, as a nuclear physicist, it is a particular honor, not just because of the field, but also because I have been working at the Research School of Physical Sciences, which Sir Mark Oliphant founded, and I've done that for 30 decades using accelerators at the ANU. So typically on the Research School of Physics, in October, celebrates Founders' Day. And that was when Sir Mark Oliphant was alive. And as a young postdoc coming in to see this very dignified gentleman who was a great physicist with a thatch of white hair sitting on the front row, intently listening to all the talks, that was a sight. And I feel sorry now that I never gathered up the courage to talk with Sir Mark Oliphant. Now, Sir Mark Oliphant was a physicist and a brilliant experimentalist with incredible technical and engineering mind. This combination is what led to the major discoveries that he was associated with. So his contributions to nuclear physics, the discovery of fusion, discovery of two isotopes, one of hydrogen, which is the triton, and the discovery of helium-3, and the mass measurements. But all that was enabled because he designed these accelerators, which are electrostatic accelerators, which led to these pioneering discoveries about the structure of the atom. The first proton synchrotron was also designed by Sir Mark Oliphant, again, with a huge range of uses, as you will learn in the second half of this lecture. But the applications part, again, as Oliver has just pointed out, a major contribution because he thought of ideas which were beyond the current technological limits. And one of that is the idea of microwave radar. And before Sir Mark thought about that, the radars were typically, didn't have the resolution. They were 10 meters to 13 meters wavelength, which meant the resolution was of that order. But he came up with an idea of using high-powered microwaves. Immediately, the idea would lead to a 100-fold increase in precision. And that was a major contributor to all the applications, including the microwave ovens that we use today. The foundational principle of it, whenever you think of popping corn or the easy dinners that we heat up in our microwave ovens, is because of that. There is a small element in that which is producing these intense microwaves. But today, we are talking about nuclear physics and accelerators, so we will focus on those two aspects. Which leads me to why, how did Sir Mark Oliphant get into nuclear physics at all? So it was a very interesting journey because he wanted to do medicine or chemistry. What a loss it would have been, again, for medical sciences and chemistry. But what happened? So what happened during that time is because he needed to earn some money, and he was given a project, a research project, but also the fact that he had great teachers and educators, and that together with the ability to do some hands-on research or focus research led him to physics. And which makes me realize that how many of us have been influenced by our teachers and educators and the enormous role they play in our life in shaping our career, and which is particularly true now when there is decreasing interest in science and technology among the students. So our teachers play an enormous role in that, as does the ability to bring some research experience into students. But so that's the lead into physics. So Sir Mark Oliphant went on to do a physics degree. The next part as to how he came to be a nuclear physicist is also very interesting, which tells us, that he attended a talk by Sir Lord Rutherford, who was visiting Australia, and he gave a lecture in Adelaide. And in Sir Mark Oliphant's words, this is him speaking about Rutherford, his words and his personality electrified me. I determined that I find a way of working in his laboratory. And once you set your mind, you will do it. And that's what happened. So Sir Mark Oliphant went to work with Rutherford later on. Now, Lord Rutherford was, in 1911, had discovered the atomic nucleus. Together, and that happened because his students, Geiger and Marsden, were looking at scattering experiments, and before that, the atom was thought to be a uniformly charged object, positively charged object with electrons embedded in it, and therefore giving it a net zero charge. That's our view of the atom. Now think about that radical change that happened because of the experiments that Geiger and Marsden did under the guidance of Rutherford, which is that the atom was not like that at all. It totally overturned the idea. What Rutherford sort of conjectured is that all the mass of the atom is inside in a very tiny volume, which you call the atomic nucleus. To give just an idea about what we are talking about, imagine we are a sporting nation, so we have to talk of stadiums. So that the volume of the atom is as big as the Melbourne cricket ground. The nucleus will be a sugar cube, which is at the center of this. That's what we mean by the center of the atom. And the strange part is that it contains 99.97% of the mass of the atom. So that's the atomic nucleus. And all the electrons are in a cloud bound to the nucleus by the electromagnetic forces. So each one of us, made up of these atoms, we have all this nucleus, tiny, dense object sitting in all of us, in all the atoms that we are made up of. Now, so that's the heart of matter. But when we go to the beach, in visible light, we see water, sand, trees, but all of us, including all these objects, are made up of atoms. The visible light does not have enough resolution to see the atoms, because the wavelength of visible light is in several hundred nanometers. To see atoms, for example, silicon and oxygen, which makes the sand, we need something more powerful, which has a better resolution, which is an electron microscope. And that allows us to see atoms, which are 5,000 times smaller than typical molecules and the sand on Earth that we see. Now, remember, the nucleus is in the center of the atom and it's very tiny. How tiny? You have to go 10,000 times smaller than the atom. No, not the most powerful of electron microscope won't let you see the nucleus. For that, we need something very short wavelength, which is where particle accelerators come in. And that's why we need particle accelerators to get to the heart of matter. So how small, I can say small, but how small is the nucleus? We line up 5 billion nuclei, and it'll come to the thickness of human hair. That's what that number, 10 to the power minus 14 meters, means. And that we can access these smaller scales if we need shorter wavelengths, and that's what speeding nuclei do, and that means the accelerators give us high enough energy to cause these nuclei to speed, which gives us short enough wavelength, and that means increased resolution. So that's why accelerators played a big role, and indeed, Sir Mark Oliphant came up with this accelerator design. Like typical accelerators, it'll have a source of ions, in this case, hydrogen. We accelerate that ion by, in this case, 300,000 volts. At the end, the speeding ions are directed towards a target station. So it's like a missile coming in and hitting a target. And that's where the nuclear reactions or the study of the nucleus is taking place. And that was a revolutionary thing. This is called an electrostatic accelerator because it uses electrostatics to generate the voltage. And the other type is the cyclotron that we heard about when Oliver was talking. This is a picture of that accelerator. The accelerator is just behind the main wall. And Cavendish Lab at that time was a great place to be. Incredible discoveries coming one after the other. But this picture is important because just look at the lab. Look at the ingenuity of people putting together all these sort of seemingly not fancy objects and making an accelerator and understanding the structure of the atom. And Cavendish was known for string and sealing wax lab. And I would wear that with pride, actually. But the only problem, sometimes mishaps can happen. So when they were getting up to this 200,000 volts, in the initial stages, the leakage current through this wooden table caused the wooden table to catch fire. So clearly, I felt right now in this day and age, they didn't fill out the work health and safety form. So it's an interesting time. But this incredible place was pushing out so many great physics ideas. At that time, so Mark Oliphant has the accelerator. Deuteron, or heavy water, has been discovered. And there was a gift from the discoverer of this heavy water, Lewis, to Sir Mark Oliphant and Lord Rutherford. So now gifting is another thing which we like in research, right? Because we don't have much money around, so any gift of precious thing is useful. So, but they made it into a great, they made great use of this. So this is a deuteron, which is heavy hydrogen. It was used as an accelerated particle as well as the target. So they fired this deuteron onto another deuteron. And Sir Mark Oliphant's accelerator was not as high voltage as the Cockcroft-Walton accelerator, which was used to split the atom, but his accelerator had high beam current. That means intense the number of protons per second or number of deuterons per second is large. It had a very fine beam. That means you could do studies, detailed studies of nuclear reactions. And then that's exactly what they did. So they did this nuclear reaction, and what they found, that two particles came out. And using the detector that they were using, they could figure out that there are two particles which are proton and triton. They were same charge, but two different isotopes. And this was the discovery of triton, which is associated with Sir Mark. And the interesting thing was that these two charged particles emerged with much larger energies than the initial energies. So how may we understand that? So imagine a pair of scales which can measure nuclear masses. So essentially what they saw is the sum of the mass of the two deuterons is more than the particles that were being produced. Now let's think about Albert Einstein's mass energy equivalence. So what they worked out is that the difference in mass must be coming out as energy, and that's why the two particles had higher energies coming out. So essentially that meant when we add back that energy, the reaction balances out. This was this recognition that energy is being produced in this nuclear reaction was the energy generated in fusion, which is the fundamentals of our aspirations to have nuclear fusion, like what happens in the sun on Earth, the International ITER project, which is an aspiration at the moment, but opens up avenues for clean energy in the future. This is an experiment at the Cavendish lab, where they split the atom, proton beams coming on to a lithium target, two alpha particles or helium nuclei being produced. This is the first time we have elements which are produced which are not the starting element. First time, elements are being produced by humankind in the laboratory. So these are foundational experiments at Cavendish. The Royal Institute put a lot of effort into popularizing science and taking science to the masses. This picture shows a lecture being given by Rutherford, and right next to him is Sir Mark Oliphant. They have brought the accelerator that Sir Mark designed from the Cavendish to this lecture hall. And they are demonstrating the splitting of the atom live in front of an audience. Let's not talk about work and safety here, but okay. So the two icons, scientific icons from Australia and New Zealand, going and understanding the importance of communicating science to the public. An extremely important part, which is still true today. So inspired by that, Ed and I thought, oh, well, we'll bring our accelerator to the Shine Dome. Only problem is, so with such a tall accelerator, we are not able to bring it here, but we leave you with an aerial photograph. But this accelerator and the accelerators that came all around the world have done and continue to do frontier fundamental research and research which benefits society. To take us on that journey, my colleague Ed Simpson will be next. Thank you.
Thank you, Nanda. And just to remind you, questions will be at the end of both talks. Nanda's given us a fascinating account of Oliphant's development, his extraordinary practicality and inventiveness, and also a lesson in how to understand scale. Now I want to introduce our second speaker, Dr. Edward Simpson. If you'd come up, Ed. Ed is a nuclear physicist, senior lecturer in the Department of Nuclear Physics and Accelerator Applications at the ANU. He works also on nuclear collisions and how they can be used in fundamental science, from quantum mechanics up to what's happening in stars like our own. He's seeking to build a bridge between this foundational nuclear science and all the applications from medical science to possibly fusion power for always 15 years in the future.
Thank you, Oliver, and thank you, everybody, for coming today. So Nanda has set up rather brilliantly the discovery of fusion and where everything started from, in some sense, in nuclear reactions. And what I want to do from there is talk about what happened in fusion over the preceding 90 years. And one of the things that Nanda mentioned is that when fusion happens, what you do is you produce a heavier element, and often that process releases energy. And fundamentally, that is the mechanism by which stars work, and it's the mechanism by which everything around us came to be made in stars and astrophysical things that happen in the cosmos. So, so creating the cosmos, how nuclear fusion made the elements. And we have to go right back to the start of time, in some sense, or at least a few minutes after it. And a few minutes after the Big Bang, we don't actually have very much. So this shows the periodic table. And the elements that you can see in white are those that existed a few minutes after the Big Bang. And there's not very much there. Some hydrogen, a bit of helium, and a very small part of lithium, which is unfortunate because we wouldn't exist very well if that's all we had. But fortunately, 200 million years later, stars emerge. And stars are really the engines of producing everything that is around us. And we've already discussed that they are powered by fusion reactions. The reason that stars shine is that within stars, nuclear fusion reactions are happening and those release energy. So during the main lifetime of a star, stars are mostly made of hydrogen to start with. Well, always, in fact, but hydrogen forming into helium, so that's a series of fusion reactions and then beta decays. It's a network of reactions. It's not a single reaction. But you can convert hydrogen into helium, and that process releases significant amounts of energy. And that's essentially what Oliphant was doing with that first deuteron-deuteron reaction. During the main lifetime of the star, you burn through hydrogen, and as the hydrogen begins to get exhausted, stars start to burn helium. And that has a slightly tricky step where you take 3 helium nuclei and you fuse them simultaneously to form carbon in something called the triple alpha process, something that we've studied here at ANU. That reaction is super important in bridging the gap from helium, which is atomic number 2, to carbon, which is atomic number 6. And there are some good reasons why you can't do anything in between, but that then proceeds through to a series of alpha fusion reactions to produce heavier elements. So you first produce oxygen, and then you produce neon. And this alpha fusion chain keeps occurring towards the end of the star's lifetime to build up gradually heavier and heavier elements. And once you get through the main lifetime of the star, when it exhausts its hydrogen, you've made quite a lot more, which is, again, that's nice for us existing. So made in the normal lifetime of stars, you can make up to about iron. So iron is element 26 in the middle there. The issue is, once you get beyond iron, fusion reactions start to absorb energy. If you remember those scales that we had at the start, the products of the fusion reaction were lighter than the things that you were fusing to start with. Once you go past iron, it turns out that they're heavier. And that means that fusion reactions absorb energy rather than emitting it. So it no longer becomes a viable method to power a star. And then complicated things happen to do with stars collapsing, and you get supernova occurring, or in principle, you might get neutron stars merging. And those are the processes by which everything else gets made. So how do we know everything else gets made, and is there any evidence that we can find? So this tells the story of some work that's done by my colleagues at ANU. And let's look at the Crab Nebula. So the Crab Nebula is what's called a supernova element. There was a supernova that occurred in 1054, or at least it was observed on Earth in 1054. It was a long way away, so it probably happened a few million years ago. But the supernova was observed first in 1054 on Earth, and it appeared in the sky as a very bright star. And early astronomers observed this new bright star that burned very brightly and then gradually faded away. And that was the supernova that led to the Crab Nebula. The Crab Nebula is the ashes of that supernova. It's the things that were produced. And now, more than 1,000 years later, it's 11 light years across, and it's getting bigger at 1,500 kilometers per second. So how do we know that this process produces elements? So suppose there is a supernova that occurs relatively near to Earth. The ashes from that supernova get emitted, and Earth passes through those ashes. And some of those ashes land on Earth. Now, it turns out that a lot of those elements that are produced in a supernova might be radioactive. And a good example is iron-60. So that's got a half-life of 2.6 million years. The iron-60 is produced in a supernova, it propagates through the universe, and then it lands on Earth. When it lands on Earth, it might land in the oceans, and then gradually it sinks to the bottom of the ocean, and then gets deposited in the crust and incorporated into crust elements on the seabed. So what we can do now is, not me personally, but we can go to the bottom of the ocean, we can dig up some crust, and it looks like this. This is a photo from this work that was done at ANU in collaboration with colleagues at Dresden. You have this kind of crust that develops over time, such that if you look at the layers of the surface of that crust, you get a time record of how that crust was created. And so if you dig further down, you go further back in time, roughly about 10 million years. And what you can do is look for iron-60 in each of those layers to understand whether or not there's a signature of Earth passing through a supernova debris remnant at some point in the past. And if you see any iron-60, it's a very clear signature because of the half-life of 2.6 million years. Any iron-60 that was here when Earth was formed long since decayed away. So if you find it, it's a very clear signature that we recently passed through a supernova. Now, it's hard to do. I haven't got another picture of the MCG, but if you fill the MCG full of salt and you add 2 grains of sugar, it's like trying to find those 2 grains of sugar. So you need enormous precision, and you need to get rid of all of the background that might be there, the background being other stuff of the same mass. And we do that using the accelerator at ANU. So this is the heavy ion accelerator facility. This is the inside rather than the outside. It consists of a 20-meter tall, 15 million volt tandem Van de Graaff. It's a big accelerator. It makes ions go fast. And the way that you detect iron 60 with that is by using a whole bunch of ways to get rid of the background. So you have an iron source, which is a thing that makes a negative ion that you can then accelerate. And my colleagues do some amazing chemistry to start getting rid of the background before they even put it in the iron source. You then accelerate it with the accelerator, and you have in the middle of the accelerator what's called a stripper foil, which gets rid of any molecular contaminants. And then you have essentially magnets. Oops. I've broken everything. Oh, is that working? Okay, here we go. So then you have magnets, and magnets are good because they bend ions based on their mass and their energy, effectively. And so you can use that to reduce the background further. And then we have a gas-filled magnet, which does the last identification. And this allows us to find those 2 grains of salt in sugar in the entire grain, mcg's worth of sugar. And what they did, I should say that we've got the highest precision for iron 60 in the world. It's the best lab to do it. What they did was this. So this graph shows the iron 60 deposition rate, so atoms per centimeter cubed per year on Earth, versus time. So that's that time record as you go back in time from today to 10 million years ago. And each point represents a sample, a layer of crust or rock taken from various repositories. And what you see is a peak. So around 2 to 3 million years ago, there's this really distinct signature of a peak of iron 60 that can only have come from a supernova. So it's, I mean, in some way it's kind of a trivial thing to say, well, yes, we know that things are being produced in the universe, but it's also that, they happened to have occurred relatively nearby. And so understanding, one of the big questions that we have in nuclear astrophysics is understanding the frequency of the events that that produce all of these elements. And so this is the sort of work that can give us some evidence for that. And it's kind of cool that we can dig out the supernova from the bottom of the ocean. And these are all my wonderful colleagues at ANU that have been doing that work. So a slightly different story is not one of us discovering or understanding how elements get made in the cosmos, but understanding how to make elements here on Earth and probing what existence. So how big a nucleus or how big an element can we make? How big an element can exist? And fusion is the way to do that, right? And it's the way that has driven our quest to discover new elements for the past 90 years. We go back to our periodic table of the elements. The ones highlighted in white now are artificial elements. They are elements that don't exist in nature and have been produced artificially by human beings with particle accelerators. And a lot of those are at the bottom. So they're all typically quite heavy elements that don't happen to exist in nature, largely because most of them are radioactive. And because they're radioactive, if they were produced at any point in the cosmos, they would have decayed away before we actually get to see them here on Earth. And all of them are produced using nuclear reactions. And so it's useful at this point to say, well, how has nuclear fusion progressed since the discovery in 1932? So in 1932, we could fuse deuterons together. They're very light isotopes, but we understood that the mass differences leads to a release of energy, and the likely that this fusion process, or this sort of fusion process, was what powers stars. And then progressively, what happened was our accelerators got bigger, which meant that we could fire nuclei with higher energies, and that allows us to fuse to form bigger elements. So we started producing heavier and heavier elements by virtue of the fact that we had bigger accelerators that allowed us to do it. And then in the 1990s, there was a kind of revelation that we suddenly understood that actually quantum mechanical effects are super important when it comes to fusion. And specifically, Schrödinger's cat, which you may or may not be familiar with, but it's about the idea that in quantum mechanics you can have a superposition of states, right? That a system can exist as a mixture of two things at the same time. And it turns out that in nuclear collisions, you can excite the nuclei as the two approach each other. And that excitation means that you end up with a superposition. And that superposition can change fusion probabilities by a factor of 1,000. So these quantum mechanical effects, beyond tunneling, become super important as you're moving to heavier and heavier nuclei. And so that story of our changing understanding of fusion and our changing techniques in terms of the accelerator has a direct influence on our discovery of the elements. So this graph shows the number of elements that have been discovered by humanity as a function of time. Right back into 1750, where we discovered about 25, up to 2024, where we've now discovered 120. This graph goes upwards, 120. That's wrong, it's 118. Sorry, I don't know why I'm saying 120. So David's shaking his head at me, and I don't know why I said 120. And then maybe I'm being very hopeful. Okay, so the interesting thing about this is obviously it goes up because we keep discovering more elements. But it's also non-linear, right? I mean, it goes in fits and starts. And it goes in fits and starts because the techniques for which we've discovered elements by have changed. So for example, from about 1900 to, I guess, the early 1930s, there was a period where we discovered lots of elements from rare earth elements and actinides due to the chemistry techniques and the sorts of places that we were looking for those elements. And then that sort of petered out, right? I mean, we'd eventually discovered all of them that we could via that technique. And then you see a sudden burst from the early 1940s where we start to use particle accelerators to discover new elements. And they were discovered either through neutron fusion reactions or reactions with light ions like alpha particles and eventually things like oxygen. And then we have another burst that starts maybe in the 1980s of what we call cold fusion. Now, cold fusion means producing the fused product at low excitation energy. But it's a technique where you use relatively heavy ions in a fusion reaction to produce something. And then the last few elements are produced with hot fusion, using a calcium-48 beam. It's a particular beam that happens to be very good for producing elements for reasons that we don't fully understand. But the interesting thing here, well, not the interesting thing perhaps, but you'll note at the end of this graph there is a plateau. And it turns out the last element we discovered was in 2009, and we haven't discovered another one since. Which, in the context of this graph, is a strong indication that we need to do something to advance our understanding of fusion, and/or we need some different technique to produce the next element. So that's what I'll talk about a little bit next. And in fact, this period is soon to be the longest period for which we haven't discovered an element since 1750. So it's high time for some change. So the way that we probe these sorts of reactions, because at ANU our real strength is understanding what's happening in terms of the nuclear reaction mechanisms, is using devices like this. So this is the Canberra Universal Binary Event Spectrometer. It's designed to measure reactions that compete with fusion. So when two nuclei fuse, there's a high probability that they'll fall apart into two objects again very quickly. And that's what this is designed to measure. The beam comes in, and we've got these two big multi-wire detectors that allow us to, well, three big multi-wire detectors now that allow us to measure pairs of events, and that allows us to very precisely reconstruct what's going on in terms of the reaction. And the sorts of things that you can deduce with it are this. So this graph is a bit complicated. It shows the fusion probability that's been measured relative to what we expect theoretically. That's on the vertical axis, and on the horizontal axis is what's called the charge product. But you can kind of read that as you progress towards the right-hand end, you're fusing bigger things together. And as you fuse bigger things together, the fusion probability is getting lower for reasons that we don't fully understand. So we've directed a lot of work recently into trying to understand this phenomena because it's going to be key to discovering the next element. And instead of asking the question, why don't nuclei fuse? We ask the question, what happens when they don't fuse? So we take a beam from our accelerator and we fire it at a target, and we look at cases where that nucleus doesn't fuse with the target. And we measure the mass and the energy and the charge of the things coming out and ask the question, well, what is it? If it's not fusing, what's happening there? And we try to understand what the processes that are occurring between those two nuclei as a function of the distance between them. So this graph shows, in a slightly complicated way, the probability of different sorts of events happening, right? So the horizontal axis here is what we're calling the effective change in kinetic energy. It's how much energy is available there for two nuclei to fuse, relative to how much there was to start with, okay? So if you just have our beam approaching our target, nothing changes. And we've got all of our kinetic energy available, which means that the two nuclei are likely to fuse. But then we go away and measure what happens in this reaction, and we deduce this effective change of kinetic energy, and we get something like this. So instead of having a nice peak that says our projectile and target are the same as what we started with, we get this whole distribution of different events where the two nuclei have lost energy. And that loss of energy is what's stopping them fusing. So understanding the precise mechanisms behind this is kind of key, because every time we lose some kinetic energy, it's like we're pushing that projectile nucleus further away, and it's less likely to engage and interact strongly with the target nucleus, less likely to fuse. And so we can also then probe, because we measure the mass and the charge of the nuclei that come out, we can also look at their identity. So what is the nucleus that comes out? And we can look at the number of nucleide pairs that we see coming out of a given reaction as a function of distance between the two nuclei. And as that distance between the two nuclei gets smaller, it turns out that we produce many, many more different sorts of nucleides. And that's due to nucleons being exchanged between the two. And we don't understand this process fully, but this has been the first indication that this sort of complicated process is happening, and that we need to understand it in order to understand fusion better, in order to understand how we can make new elements. So in 2024, things are much more complex than they were previously. And there are lots of open questions. We don't know when these nucleon exchanges happen. We don't know how it really impacts fusion yet. There are all sorts of slightly more abstract questions about the nature of irreversibility in quantum systems that are isolated. So if we've got two nuclei colliding, there's no way that those two nuclei can to interact with anything else for the duration of their interaction. And in quantum systems, we don't understand how irreversible outcomes can arise from that sort of process. That's a bit abstract. But the main question at the end there is, will we ever discover a new element? And if so, how? I'm kind of confident that we will. I mean, the story of element discovery has all been about better understanding of what's going on, technical advances in terms of accelerators, and technical advances in terms of how you detect nuclei. And a really good example of that is maybe the proton synchrotron. So the proton synchrotron at Birmingham was the first ever proton synchrotron built, and it was designed and the construction started by Sir Mark Oliphant. And this picture's taken in 1953, but they started construction in 1946, which is just 12 years after they discovered fusion. And in that time, the scale has changed dramatically. So you've gone from an accelerator that accelerated protons to 200,000 volts, 200,000 electron volts, to accelerators that will go up to 1 billion. So it's gone up by a factor of 5,000 in just 12 years. And the scale of the accelerator going from a benchtop device to an accelerator that used an 800-ton magnet is kind of incredible, right? So this is an astonishing pace in pushing those boundaries, and it allows people to do amazing science. Now, Mark Oliphant, he was kind of the originator and did a lot of technical development on the concept of a synchrotron, which has got resonances down the years. It's now the basis of the Large Hadron Collider at CERN. So it's a really important kind of design for an accelerator. And also, we are hopefully getting one in Australia soon. So this is the Australian Bragg Centre that's under construction in Adelaide. It will hopefully be Australia's newest accelerator, and they're going to use a proton synchrotron here. But the Bragg Centre is not about doing fundamental physics. It's about using beams of protons to treat cancer in form of radiotherapy. So the idea is that you shoot a beam of protons into a patient, and they stop in a tumor, and that stopping in the tumor kills tumor cells and helps cure people's cancers. So proton therapy is a relatively new technique, and this hopefully will be the first centre in Australia. It relies on a principle that was done by another Australian physicist, William Henry Bragg, and the Bragg Centre is named for him, but it relies on the fact that photons, which are X-rays, and protons interact with matter in a very different way. So if you shoot a photon beam, an X-ray beam into a patient, it deposits most of its energy at the surface, and then the energy and the dose delivered decreases as it goes further in the patient. So if you have a tumor that's at some depth in the patient, the photon beam is actually putting a lot of dose into healthy tissue before it gets to where you want to actually hit with that dose. If you've got a proton beam, the way it deposits energy is very different. It has this Bragg peak where it gradually slows down, and then most of its energy gets deposited near where it stops. And that means that you get more dose in the tumor and less dose in the tissue. And that's very good, particularly for tumors where you don't want to dose stuff behind the tumor, if it's like head or neck, but also in pediatrics where you just don't want to dose the patient if you can avoid it. And that's going to rely on a proton synchrotron that was Mark Oliphant's invention. So I think those technical developments kind of resonate down the years, not just in terms of the science and the physics, but also in all these applications that emerge from them. And to do all of that, we need to understand a lot of nuclear physics, right? So this is my conception of putting a proton beam into a body. 200 MeV proton beam travels maybe 20, 25 centimeters in the body. And along the way, a lot of nuclear physics can happen. So that proton can interact with nuclei in the body. Nuclear reactions can occur. And the important part is that that changes where the dose goes in the patient. So you need to understand all of the nuclear physics that might happen along the way in order to make sure that you know where the dose is going when you're treating a patient and that you're not underdosing or overdosing. And lots of complicated things can happen that we understand with a whole variety of different models, underpinned by nuclear structure and all of the quantum mechanics that's involved. Okay, so I think here we've just touched on a few of Sir Mark Oliphant's scientific achievements. He discovered fusion, which is the basis of nuclear astrophysics and our understanding of how everything got made in the universe. He designed accelerators, not just the one that he used to discover fusion, but the proton synchrotron. And those clearly have resonances down the years, like now we're seeing in terms of proton therapy, cancer, and also in the largest accelerator in the world, a Large Hadron Collider. He didn't win a Nobel Prize, but potentially could have won 2 for his developments. And he had a profound impact on Australian science in particular, both as the first director of the Research School of Physical Sciences and as the founding president of the Academy of Science. He was an outspoken advocate for science and mathematics, and I think that's perhaps his most important and enduring legacy. So thank you.
Thank you. Don't go away. Well, Ed's given us a fascinating picture of a lot of more things that have happened more recently, but all relating back to the extraordinary achievements of Oliphant more than, 80 years and more back, and then bringing it out here to Australia. But now we're going to have question and answer. So Nanda's here, Ed's here. Please just raise your hand here if you have a question.
Thank you. You're right. This is to the second speaker. Why have you got confidence that there are heavier fusion products? You say that you implied that it's just merely a matter of having better detection or higher energy. There must be some limit. Why do you have that confidence?
Yeah, that's true. I mean, in principle, there will be a limit. So you can ask the question, what happens to these nuclei after you form them? And how do we actually even detect that they existed? So the way that you do that is that, you have this fusion reaction occurring, and then you have a magnetic spectrometer. But the idea is that you embed those fusion products in a detector, and you wait for them to alpha decay. And the idea is that they alpha decay, and the daughter products alpha decay, and by mapping back this series of alpha decays, you can say, okay, that's how we made a new element. There may be some point where these nuclei just fission, and at that point, it gets very difficult to identify that you actually made them, even if they do happen to live a relatively long time. So there will be certainly a limit on the practicalities of identifying these nuclei when they exist, and there will also become a point when their half-lives are so short that measuring them at all becomes quite difficult. I don't think we're at that limit yet, so the next elements are 119 and 120, but at some point we will hit that limit.
Down here.
One question was, how long does an element need to exist for it to count as a new element, and how hard is it to make the heaviest elements that exist?
So how long does it have to exist to count as an element? Probably the detection limit is really the key question. Ultimately, you have to be able to detect it to say that it existed to some extent, and you have to be able to detect it in an unambiguous way. And so alpha decays give you a way of doing that. You're limited by, ultimately you're limited by the flight path. It's technical, right? But you're limited by how the flight path from where you produce it to where the detector is, because you don't put the detector right by the thing, the the target because you just get all sorts of crap in the detector. So you need to have a magnetic spectrometer to separate it, and there is a flight time between there and where it gets in the detector. That likely, I presume, the limit will be that they start fissioning rather than the flight time is the limit, but Nanda might have an opinion.
Well, the other question about element, when do you call it an element? When an atom is formed, which means I have to capture the electrons. So it has to live long enough for the electrons to be captured for it to become an atom, which will be perhaps 10 to the power minus 18 seconds or more. I don't know, something like that. Maybe longer.
A question for you both, and I'm not confident enough about the science to ask you a scientific question, but I was interested politically. You said that Sir Mark didn't win a Nobel Prize. Given that he discovered fusion, why was that? Why didn't he win a Nobel Prize for that?
I think for fusion, the issue was probably that there were just too many things going on. There was a lot of competition for Nobel Prizes because there were so many amazing discoveries in that period that just stood out. And in that context, it was. I guess the issue was was fusion worthy relative to all these other things? I think in another time, he may well have won one for fusion. And I don't think there was ever a Nobel Prize awarded for the invention of the synchrotron, but there was for the cyclotron, and it's kind of an equally important form of accelerating technology. And if there was one awarded for the synchrotron, he probably would have deserved a share in it.
I think it's fair to say that historically many great physicists have missed out. A German physicist, Arthur Sommerfeld, was nominated, I think, 80 times by senior colleagues and never got one. So I don't know if Oliphant was nominated very many times, but he's not the only one. Could you say a bit more about health, Ed? Just, these new things, they're proven in practice, but is it a big bet on the part of South Australia to get one of these things there?
Not in terms of health outcomes. Like the health outcomes for proton therapy are pretty robust. It's all to do with the physics of the Bragg peak to some extent. You can get more dose in the tumor and less in the healthy tissue, and in general, that's a good thing. You wouldn't necessarily, you wouldn't treat every patient that needs radiotherapy with proton therapy because it's a bit more expensive, but it's a lot cheaper than sending patients overseas to get the same therapy. And for particular types of cancer, it's much better. The health outcomes are much better. There is some question around carbon ion therapy. So instead of using protons, you can also use a beam of carbon ions, and they are. So, for example, in Japan, they've been doing that for a couple of decades. There are, in principle, some benefits there because you get even more dose deposited in the tumor, and because carbon ions are heavier and they've got a higher charge, you're more likely to get what are called double strand breaks. So the idea of damaging the tumor is to break the DNA of the tumor cells. Because carbon ions are heavy and they're highly charged, you're more likely to break both strands of DNA, and then it's much less likely to repair itself. But it's very difficult to do clinical studies that are kind of meet the sort of clinical standards that you would get for drugs, because almost always they just say, oh, well, actually it just works a lot better. And so they try and get patients using it. But
and if I may add, there are aspirations of getting proton therapy accelerators elsewhere as well. I think Queensland had plans as well.
Are there any questions for? There's a question there.
Thank you. So some elements are inherently unstable despite being in the bulk of the periodic table, like promethium. There are heavier elements that are stable, while promethium, there is very few of it actually existing on Earth. So if you had to guess, is there a chance that we would encounter more stable elements down the line past the 118 atomic number?
Great question. One of the reasons that the majority of the elements which are very heavier are not stable is because, imagine scrunching so many protons inside a tiny volume that the nucleus is, right? So that's why we don't get naturally occurring sort of heavy elements beyond uranium, because that's the limit, beyond which the protons just want to separate out. Now, the reason that they're held together is the strong nuclear force, which is a glue holding all these protons together. The reason that the heavier elements might exist is something because what Ed alluded to, which is quantum mechanics. So did you want to carry on with that?
Yeah, sure. I mean, so if you think of the periodic table, you've got the halogens, right? The noble gases. So the noble gases are particularly stable chemically, and they don't like to bond to other things because they've got a closed shell structure, right? So all of their electron shells are filled. And we have a similar concept in nuclear physics because protons and neutrons exist in shells and nuclei. And every time you get a shell closure that's filled, it adds to the stability of a nucleus. So one of the main goals of heavy element research is to try and reach something called the island of superheavy stability, which is a predicted point somewhere above where we can get to, where the nuclei happen to have closed shells, and those closed shells then increase their half-life, and it makes them live for longer. Now, the tricky part is that those isotopes happen to have lots of neutrons, and we don't have ways to use accelerators to get those neutrons into them currently. But that's certainly a goal. So they won't be stable, but they may well be much longer lived than some of the heavy isotopes we've already discovered.
Are there any questions from the people online? No, well, got one more question here from a person in the hall.
Hello. I like that he went to Rutherford's lecture and was so gripped by what Rutherford was saying that he went, that's it, physics is for me, let's go. What's the modern equivalent of doing that?
You being here, we expect you.
I've somewhat left my 20s behind. Thank you for the perhaps a stronger prescription.
No further.
Well, I can't, it's not recent, but the reason I went into physics is because I went to a lab where I saw this huge magnet, which was like, wow, that's a magnet? Because I had only played with these little bar magnets. I think to be able to actually see things, and that's the reason I think the vacation scholarships or work experience is an important part, because in my view, students have, or most people have, a certain view of research, everyone wearing white lab coats and sitting in a corner and doing things. That's not how it is. Theoretical physics may have a different sort of way to attract people, but I think the foundation science is always an attractor. It's always foundational science, dark matter, astrophysics, you know. So I think foundational science together with hands-on ability to, or hands-on experience is a motivator.
Ed, perhaps you'd like to add how you got into physics.
Yeah, that's a good question, actually. I don't know. I think I always wanted to do physics. I had a good physics teacher, right? And that helps a lot. And probably why I always wanted to do physics. I mean, I think certainly, I did my PhD in the UK. Something that certainly helped around when I was doing my PhD was they were effective science communicators that were on TV, right? I've forgotten his name now. No, say it again. No, Johnny Ball. No. Oh my God. How have I forgotten his name?
More?
Yeah, so Jim Al-Khalili was, I went to university, sorry, so Jim Al-Khalili I know very well. So he was one, right? I mean, he was making all these TV programs. And the guy from Manchester, whose name I've forgotten, a shame. Brian Cox, that's the one. So, and obviously they didn't have a very great influence on me. But we did see a significant uptake in the number of students coming into physics. And particularly we saw them through Surrey, partly because Jim Al-Khalili was there. Whether Australia has that in the way that it needs, I don't know. I mean, Australia, well, I don't watch TV, so maybe I'm not very helpful in that regard. And maybe nobody watches TV anymore, and we should be talking about TikTok. But I think having people that can effectively communicate science and are supported to go out and do it, which I think Australia is pretty bad at, it's almost impossible to get funding to go out and talk to people about science to some extent. And I think that's the way to do it, right? You need to talk to people, and you need to show them what you do, and you need to see them you're a human being, not a lab coat. And we should do it more, I guess.
I think that's a very good point, that we have to, science is just as much about people as it is about concepts and things. If I could put a personal note in, a very great statistician and evolutionary thinker, R.A. Fisher, retired to Adelaide, and he came to live with my family, and that's turned me into a statistician who finished up in evolutionary biology. Now, not everybody approves of Fisher these days, but he was a great man, a great thinker, and a wonderful guide for a schoolboy, which I then was. But no, I'd just like to thank Nanda and Ed very much for their inspiring talks. There are some actual school people here today, so I hope they're suitably inspired, even if they're going to become famous musicians or the like, that they still take home a message that science is about wonderful people. And so thank you all for coming tonight. And I should mention that the final talk in this series is on the 10th of December, also Tuesday. And those who've signed up obviously will hear about it automatically, but if not, look on the web or whatever for it, because it's the last one and it'll be really good. And thank you all, and good night.